Alrighty, gang, welcome back. I'm excited for us today because we are entering into this topic of related rates, which is one of those really kind of deep and profound things that we don't get to do a whole lot of. I mean, as a mathematician, I would argue that pretty much everything we do is deep and profound, but in the sense that it connects to so many other areas, connects to chemistry, connects to physics, biology. Pretty much everywhere you have an application of calculus, it is a related rate. And the term sounds vague because it is. I'll do my best to explain, but let's go ahead and jump in and get started. Okay. Here we go. All right. So this is MAC2312 section, 2311 section 004, which is Calc 1. And today is Valentine's Day, 2022. So last time we talked about logarithmic differentiation, the derivative of the logarithm function, and also how you can use logarithms to help you differentiate other functions, which either are unpleasant to work with directly, like a big nasty product or a big nasty quotient. Also allowing us to differentiate some functions that otherwise would be completely inaccessible, things like the super exponential x to the x, or other weird functions where both the base and the exponent are variable. In each of those cases, we saw if you take the natural log on both sides first, then differentiate implicitly, you can get an expression for y primed or f primed, whatever you want to call it, without having to do a big nasty quotient rule in the first case, and just through use of a little bit of product rule and algebra in the second case. All of that is kind of practice with implicit differentiation. The topic for today, which is related rates, is another big application of implicit differentiation. So let me pull up let's go to the text in the syllabus. Both of those. Here we are. So log derivatives last time, related rates today. We're going to look at a few other applications after this, but related rates, for whatever reason, tends to be one of the stickier ones. So I'm going to move kind of gently through this today, and we may talk about it a bit more tomorrow. Linear approximations, not terribly bad. And then all of the stuff that you see here in week 8 and week 9 is leading to being able to draw a graph of a complicated function without graphing utilities, basically. So being able to find hills and valleys, being able to see how the curvature changes as the derivative changes. L'Hopital's rule is a sneaky trick for some limits. And then, of course, the section that we culminate with before exam 2 is on curve sketching. I have graded most of your tests, but not all of them, and my goal is to get everything entered into the Canvas gradebook together with all of your feedback. If you go look at your written work and pull it up in Canvas, you'll see it's overlaid with like red marks. This is kind of how I give you feedback on your tests. And all of that should be in today, unless you took the test at an alternate date. If you took the test at an alternate date, it'll take a little bit longer. But today, we're going to do section 3.9. So a related rate is what it sounds like. It is when you have two different quantities, variables, which are connected through a geometry or algebra relationship. And then you can find how the rate of change for one impacts the rate of change for another. In a sense, what we've been doing when we take regular derivatives is this, right? When you find out how y prime is related to x, you're learning how changes in x result in changes for y. Usually in this context, though, we won't be thinking of y as a function of x, and we won't be thinking of x as a function of y. And this is sort of one of the first new conceptual hurdles in related rates. Generally, what we'll be doing here, so generally, we will begin with an algebra, or algebraic, or geometrical relationship between two objects, or two quantities, let's say, which evolve over time. And what we want to know how quickly one quantity is changing at a particular moment given some information on how the other is changing. The upshot here is that these are word problems, right? These are generally word problems. And they're word problems where you will use the geometry and algebra together with a certain derivative to get information about another derivative. And because these are usually word problems, not always, but usually word problems where the change is taking place not as like x moves around, but as time passes, the derivatives we'll be taking will usually be with respect to the variable t, and t here stands for time. So almost always, we will be differentiating implicitly with respect to time. And I'll use the variable t to represent time. The SI unit for time is seconds, so usually time will be measured in seconds, but always the variable t. What this means is that whatever other variables you have in your expression, you're going to treat them the same way we treated y when we learned implicit differentiation, right? So when we learned how to differentiate an expression implicitly, every time you bumped into a y, you would kind of differentiate it like normal and then slap on a y prime. And that was us thinking about the chain rule, thinking that y was implicitly a function of x. So when we differentiated, say, y squared, we would differentiate the outer and get 2y, but then we had to multiply by the derivative of the inner. And because y was implicitly a function of x, that meant multiplying by y primed. Here, we'll have x's, y's, t's, thetas, r's, a's, all sorts of different symbols. What you need to remember is that all of these things are implicitly functions of time, because we're acknowledging that the situation, whatever it is one that changes as the clock spins around. So I think that's about all the guideline that can be offered. You have the tools already. It's just really a matter of practice. And the fundamental skills are going to be taking the physical situation as it's described, drawing a good picture, inferring the algebra relationship from the picture, and then differentiating implicitly with respect to the variable t, which will not usually show up explicitly anywhere in the expression. So I'm going to begin with a nice gentle example, and we're going to spend pretty much all day today just straight up working examples. Oh. So let's say an oil rig sprouts a leak at time t equals 0. The oil forms a circle, on top of the water. And its area is growing at, let's say, 2 meters squared per second. So this means that if you're looking down from above at this oil leak, which is like sitting on top of the water, it's a circle, and that circle is growing. Its area is increasing 2 square meters every second. I want to know how far away do I need to send my cleanup crew, right? I need to send a cleanup crew out from this rig. I got to tell them, hey, you guys got to start like dropping surfactants, whatever, all the bullshit that they need to do when they poison our world like this. And you got to do it everywhere from the center of the oil rig out to the edge of the spill. I need to tell them then how far away the edge of the spill is. And that's going to change because there's always more oil coming out. We've seen these things, right? So what we want to find how quickly the radius of the spill is increasing at the moment when the area is, let's say, no, how about 10 square meters, right? And this is a fairly realistic situation. When oil does sit on top of water, as it does, it's less dense, it'll form a certain thickness, right? That layer of oil on top of the water has a natural thickness it wants to sit at. It can't go beyond that, otherwise that it would just spread out more. So one way you can actually approximate the area of such a spill is by approximating how much oil has come out. You know, it'll spread out radially, symmetrically, ignoring things like wind and waves. And you know how thick it will be. So if you know the volume of oil that's come out, you can tell me roughly what the area of that spill should be at that moment. So at that moment, I know that the area of the spill is 10 square meters. And I know that the area is growing at 2 square meters per second. This would be kind of a measure of how fast the oil is spilling out. I want to say what the radius is doing at the moment when the area is 10 meters squared. How fast is that radius growing? Is the physical situation clear? Do we feel like we have a clear picture in our head? Can we tell? Am I using like words that are coming across reasonably? Okay. So the first step to these things is always to draw a picture. And it doesn't have to be anything fancy. You'll see my art skills are not anything special. Okay, so the oil rig is right here at the center of the spill. The spill is circular. We're looking down, like flying over with a helicopter. And that spill has a certain radius. Okay, so you draw your picture. We need to assign some variables, right? So I'm assigning the variable r to the radius. That's my free choice. You can call it whatever you want. We'll call it r. And I'm going to assign the variable a for the area. And we know that a is equal to pi times r squared for a circle. This is a geometry fact that we should all be familiar with. Having done this, I like to list the things we know and list the things we want. So we know that the area is growing at the speed 2 meters squared per second, 2 square meters per second. In terms of derivatives and the variables a and r, what does it mean to say that the area is growing at 2 meters squared per second? So
Does it,
yeah, go ahead. No, good.
does it mean, like for R, we would be putting in something along the lines of R plus 2 times T?
That's 2 times t. Oh, I think I see what you're saying. What you're thinking is almost correct, and that would be one way to approach the problem. It's the area that's growing at that speed. So we could say that the area, if you wanted to find an explicit formula for the area as a function of time, we could do that. That's an option. But it's harder work than is necessary. So it would be true that this implies that as a function of time, the area's rate of growth or rate of change would be 2, right? If we're using units meters per second squared, I could write A of t equals 2t or something like that. But there's a much easier way to go about this. The rate of change for the area would be dA dt, right? That's how if you think of this as like a difference quotient, this is like a change in areas, and this is like a change in time. So that ratio is a speed, it's how fast the area is growing. And they've told us that the area is growing at 2 meters squared per second. So we can say that dA dt is 2. And then there's a nice notation for units that I like, where you put it in a bracket at the end. You don't have to do this if you don't want to. But in problems, at least where it's not too cumbersome to do that, I would. But you're 100% correct in saying that, yeah, A of t equals 2t. That would be a function that has this derivative. But we can actually get there without constructing the function explicitly. So earlier when I said that Leibniz notation is kind of necessary for certain problems, this is those problems, right? When we're talking about related rates, the Leibniz notation is really your best friend. If you are allergic to Leibniz notation, I understand. There is a notation from physics. You could call this a dot with a dot over the top. A dot over the top of a variable always means derivative taken with respect to time. But I will use the Leibniz notation, right? So a dot and dA dt mean the same thing. It's kind of like a prime, only it's a prime that tells you what the variable is. The variable is always t when you use the dot. The thing I want here is the rate of change for the radius. They say find how quickly the radius of the spill is increasing at the moment when the area is 10 meters squared. So the rate of change for the radius would be dr dt. And I want dr dt at the moment when A is 10. Let's see, I'm doing room to squeeze it in here, meters squared. So we read the problem, try to understand what's going on a little bit, draw a picture, assign some variables, and then list out the things you know in terms of derivatives and the things we want in terms of derivatives. You can probably guess what the next step is. We're going to differentiate through this expression, which will make these sort of things show up. We're going to differentiate through this expression implicitly with respect to the variable t. So let's see what that looks like. I apply the operator ddt to both sides of that algebra relationship. On the left-hand side, ddt of A gives me dA dt. And on the right-hand side, this pi is a constant multiple. It can pop out. ddt of r squared, here's a place where we need to be a little bit careful with our implicit differentiation. Remember, the variable that I'm differentiating with respect to is not r. So it's not just going to be 2r. Think of r as being like f of t. So when we differentiate r squared, we'll get 2r as the derivative of the outer with the inner left alone, times the derivative of the inner with respect to t, which is dr dt. So it's going to be pi times 2r. Right? It's like the normal derivative here. That would be the ddr derivative times dr dt. There's probably a computer RAM joking there somewhere if you look for it. Or a dance dance revolution. So by differentiating a equals pi r squared on both sides with respect to time, and doing so implicitly, we get this thing, which is called a differential equation, right? It's an equation relating two different derivatives to each other. And in MAP2311, if you take that class, you'll learn how to solve these things, not for numbers, but for functions, which could have that relationship. But that's not our goal here. Our goal is just to answer the question, how fast is the radius increasing at the moment when the area is 10 meters squared? And if we look at this differential equation, there are some things here that I know and some things here that I want. One of the things that I know is dA dt. I know that the oil is coming out of the rig at such a speed that the area is increasing at 2 square meters per second. So dA dt is always 2. And I'll go ahead and just write 2 here. I'll leave off the units. You can include the units. And if you're a chemistry, physics type person, dimensional analysis, making sure units line up can be a really helpful way to check your work. But this is a math class, so I'll stick to the mathematics. The right-hand side is 2 pi r times dr dt. And I want dr dt. I could solve for dr dt here, but there's this variable r floating around, and he's not going to go away. So what I need to do from here is sort out the value of the variable r at the moment in question. So this relationship is true for all time, right? This is true from the moment the rig starts spilling oil to the moment the rig stops spilling oil, whenever that is. Hopefully it doesn't go on forever, because if this is always true, then the Earth is going to just be oil eventually. I don't think there's that much oil on the planet, so, but through all values of the variable t for which the problem makes sense, this is a true statement. In order to get rid of this variable r, I need to figure out what the radius of this spill is at the moment when the area is 10. That's the moment I'm interested in. And if I plug that in here and then solve for dr dt, we win. So at this point, we need to figure out what r is at the moment when a is 10. Then we can solve for dr dt. And most related rates problems have a step like this, where after you take your derivative and plug in everything you know, it's like, ah, shit, there's something left over. There's something that's going to keep me from getting the thing I want. So we got to return to the original relationship and solve for one of the variables at a specific moment. So when a equals 10, we have 10 equals pi r squared, because a is always pi r squared for a circle. divide both sides by pi. 10 over pi equals r squared. And then take square roots. You get plus and minus the square root of 10 over pi equals r. I'll move this up here. How about that? When you solve this equation, you do get a plus and minus because you take square roots on both sides as one of your steps. But because of the real world situation, we know that the negative solution to this equation isn't interesting to us, right? This radius is never going to be negative. It's a distance. So we take r to be the positive square root of 10 over pi. And we're going to plug that in here. Now we go ahead and just move the page up. Say therefore, at the moment when a is equal to 10, we have, I'm going to plug this r value back in here and try to solve for dr dt. So 2 equals 2 pi times the square root of 10 over pi times dr dt. I can divide both sides by 2, and the 2's will go away. I can split up the square root here. So I'll have 1 equals pi times the square root of 10 over the square root of pi times dr dt. And before I could just divide over by this whole chunk, but I think it's nice to simplify it just a little bit first. So upstairs here I have pi, and I'm dividing by the square root of pi. That's pi to the 1 divided by pi to the 1/2. So this is the same as 1 equals the square root of pi times the square root of 10 times dr dt. And the algebra note there is because pi over square root of pi, that's pi to the 1 over pi to the 1/2. It's pi to the 1 minus 1/2 is pi to the 1/2, which is the square root of pi. All right, now we can divide over. 1 over the square root of pi times the square root of 10. That's equal to, yeah, that's your answer. So at the moment in question, this is how fast the radius is growing. If we want as a decimal, I'll hold here for a minute. Questions about the steps showing now? We're all comfy with this algebra work? And the step right here is that rule that like a to the x over a to the y is a to the x minus y. So rule for exponents. Let me make sure I'm understanding the question. So are we asking how we got this or how we got from here down to here? denominator at the bottom. So I took this relationship right here, 1 equals the square root of pi times the square root of 10, and I just divided both sides by root pi times root 10. So both of these constants are multiplying the thing I want. So if I want to get this alone, I just divide both sides by this chunk. So over here, the left-hand side is 1, and when I divide by those, it becomes 1 over root pi times root 10. Cool. Root pi, by the way, is a very fun number. He shows up as the area under a certain curve, e to the negative x squared from negative infinity to infinity. If you're familiar with the concept of the bell curve, which was this like important statistical thing that people have used to make all sorts of nasty generalizations about human intelligence, the square root of pi is the area bounded by that curve. This is it. And we may want some tangible feeling to what this is, right? It's hard to approximate that number. So that's about 0.178 or 0.18. And the units here, so the radius is increasing at 1 over root pi times root 10, approximately 0.18. And we want to ask ourselves, what units would this have? Is it, rabbits per year, miles per hour, bagels per person? And remember, the radius is being measured in meters and time is being measured in seconds. So this derivative dr dt would have units meters per second. So about every 5 seconds, the radius of the spill increases by 1 meter. That's the rough interpretation.
Professor?
Yeah.
So I think I just, there's something I'm not getting here. So how is this radius, if the radius is increasing at 0.18 meters per second here, I'm just confused on how that's different from it increasing at 2 meters squared per second.
No, that's good. So that was the area, and those are the two rates that are related to each other. So d is the rate of growth for the radius, and dA dt, which was 2, is the rate of growth for the area. And those are the two rates which are related through this geometry.
Oh, okay. All right, thank you.
Yeah, of course. No, that's cool. And that's kind of the crux of the thing. Glad you asked.
Both of these rates are constant, right?
Good question. So the rate dA dt is constant, yes. And dA dt we said is always 2. Dr dt, not constant. But what we did is we plugged in the values for A, dA dt, R, which correspond to a particular moment. So this is a good question, and it's a very subtle thing. If we come back up here, remember regarding this equation, I said this is true for all time t. This is always true. And what we're going to do is plug in the values of our variable that correspond to something going on at a particular moment in time. And that was plugging in the value for R here. So it's true that I claimed the rate of change for the area, dA dt, is always constant. Dr dt, if you solve this differential equation in general for R, you will find that R is certainly not a linear function here. It'd be something, I think, a good deal more complicated, some weird exponential. But at the moment in question, dr dt is going to be a particular number. And that particular number is this constant. So yeah, it's quite subtle. And Evan's idea of finding an explicit formula for the function A would let us get a slightly better feel for what the function r is doing, because you could then solve that, before taking the derivative for r. But no, it's not the case that r is or that dr dt is always constant. It's just the case that at this moment in time, r and our dr dt takes this specific value. That's
Okay,
a great
thank you.
question. Of course, of course. Okay. There's another classic problem like these. You can't teach a lecture on related rates without talking about ladders sliding down walls. I don't know. Don't know how this worked its way into canon, but it certainly is canon. So I can tell you that a 10-foot ladder is leaning against a wall. I don't know if you guys have ever had this happen, but sometimes when you're up on top of a ladder, the base of the ladder starts to slide out. It's friggin' terrifying, because it means you're about to eat massive shit. But the rate at which you fall is related to the rate at which the base of the ladder slides away from the wall. So a 10-foot ladder is leaning against a wall. The base of the ladder begins sliding out at time t equals 0 seconds at a speed of, let's say, 2 feet per second. And us being perched at top of the ladder are going to start coming down. How fast is the top of the ladder falling when the base is 4 feet from the wall? So we want to begin by drawing a picture, right? We all have a rough understanding of what the physical situation is. There's a wall here. There's a ladder leaned up against the wall. Here's my ladder. Here's the base of the ladder. Here's the top of the ladder. Now this ladder is 10 feet long. And I know that this end of the ladder is going to start sliding out. Sorry, my wife is calling me. Just 1 second. Okay, sorry about that. So, wall, floor, 10-foot long ladder, bottom of the ladder starts sliding out. And we know that the speed the bottom of the ladder is sliding out is 2 feet per second. So I'll go ahead and 2 feet per second. Next step is to assign some variables. So I'll say that the distance from the base of the ladder to the wall is x. And I'll say that the distance from the floor to the top of the ladder is y. And now we're at that stage where we want to write down the things we know and the things we want. And we want to do that in terms of derivatives. So what are those? what information from the problem can I write down as a derivative of y or a derivative of x in a known quantity?
X equals 4 feet.
Yeah, so that is a thing that's going to show up here somewhere, right? I want to know how fast the top of the ladder is falling when the base is 4 feet from the wall. And that's going to show up under my want here. So I want something at the moment when x equals 4. So at the start of the situation, the ladder x is smaller than 4, right, presumably. And then at the end of the situation, x is going to be 10 because this ladder is coming down. And I want to kind of freeze time and answer the question, how fast is the top of the ladder falling at the moment when x is 4? So that's going to show up in here under the stuff we want. What kind of derivative information do I know? What speed or rate of change was given to me, and what variable is that talking about?
The derivative of x is 2 feet per second.
Mm-hmm. Yeah, that's it exactly. So dx dt is 2 feet per second, right? If x is this distance, that distance is first increasing, so the derivative there will be positive. And I know that that distance is increasing at a speed of 2 feet per second. And so every second, the back end of this ladder slides 2 more feet out along the wall. I'm sorry, along the floor. And then the thing I want to know how fast the top of the ladder is falling, right? So I want to know how this distance is changing. So that would be dy dt. So I want dy dt at the moment when x is equal to 4, and I know that dx dt is 2. The next step is going to be to come up with our algebra relationship. And to that end, I would put on some purple glasses and reread the picture. I guess you can't really see the color standing out that well, can you? Sorry, this camera, not the best. There's a little right triangle in here. Right, the ladder, the wall, and the floor, assuming the building was built well, form a right triangle. So we can lean on good old Pythagoras to tell me a relationship between x and y, namely x squared plus y squared equals 10 squared. This is true for any right triangle. Right, but the squares of sum of the squares of the side lengths is the square of the hypotenuse. X squared plus y squared is 100. Right, 10 squared is 100. So now I've got all the pieces. I've got a good picture. I've labeled things, chosen some variables. I've written down what I know and what I want to know in terms of derivatives of those variables taken with respect to time. And I've cooked up a nice equation relating the original variables that I can differentiate through to make dx dt and dy dt appear. So if I take the time derivative on both sides, I almost wrote ddx. If I take the time derivative on both sides, x squared plus y squared is equal to the time derivative of 100 again, the trick is just remember you're differentiating implicitly. So x and y are both functions of time. They both get treated the same way y gets treated when you differentiate implicitly with respect to x. So this would be 2x times the derivative of the inside, which is dx dt, or x dot, plus 2y times dy dt, or y dot. And the derivative of a constant, no matter what variable you're differentiating with respect to, will always be 0. We can divide both sides by 2. You get x times dx dt plus y times dy dt is equal to 0. And that's your nice little differential equation, which we can plug into as needed. I know that dx dt is always going to be 2. So I can replace this dx dt by 2. So it becomes 2x plus y times dy dt equals 0. And now there's kind of two things in the way of me being able to solve for dy dt. There's an x here and a y here. And I need to have some numbers I can plug in for both of those. So this is sort of the relationship that's true for all time. And then I want to freeze time at the moment when x is equal to 4 and solve for dy dt. So I could plug in 4 for x, but then there would still be a y left over. So what we need to know, I'll say here, at the moment, when x equals 4, this becomes 2 times 4 is 8 on a good day, plus y times dy dt equals 0. So I still need to know y. Y when x is equal to 4. And this is kind of like the step where we had to go solve for r when a was equal to whatever 10. The relationship we started with, x squared plus y squared equals 100, that's certainly always true. So I can come back to this, plug in 4 for x and solve for y. We got 4 squared plus y squared equals 100, which means 16 plus y squared is 100, which means y squared is 100 minus 16, which is 84. So y would be plus or minus the square root of 84. And I'll take the positive because y is a length. The ladder is not going to fall through the floor. Y will never be negative. So I take my square root of 84 and plug it in right here, and then solve for dy dt. So when x is 4 feet, we have 8 plus the square root of 84 times dy dt is 0. We can subtract the 8 over and then divide by the square root of 84. Finally giving us dy dt is negative 8 over the square root of 84. And that's it. Again, this is, these problems lend themselves to a little bit of calculator work at the end, because how big is that? You can approximate reasonably, you know that 84 is a little bigger than 81, and the square root of 81 is 9. So this is somewhere around 8/9. But that's still rough, and it's still a fraction, which for a lot of people it doesn't lend itself to size comparisons quite as well. So I'll go ahead and take -8 and divide by the square root of 84 in my calculator. I get negative 0.873-ish. And again, I want to ask, what are the units here?
Feet per second.
Very good, yeah. Y is a distance being measured in feet. T is time measured in seconds. This is feet per second. Why is this negative?
Because it's falling down.
Very good. Y is decreasing, right? That height, the distance from the floor to the top of the ladder, that vertical distance is decreasing. So we expect that dy dt would be negative, and it is. And that can be a good intuition check. Did your derivative not to at least the sign it should have? Does it have the units it should have? All of those sort of things. How fast is that? Well, about 1 foot per second, right? In the neighborhood of 1 foot per second. It's not the scariest fall in the world, but it's not fun. And the truth is, you will be accelerating. So by the time you hit the ground, you're going to go faster. But we'll leave that for your kinematics classes. Questions on any of the steps we did here? Okay. There are some other kind of classic problems, like a melting snowball, and you see how fast the volume is changing. You want to know how fast the radius is changing. I like to try and show you examples that include all the different kind of geometry formulas you need, like the area being pi r squared. That's an important thing. But there's just so many different things. So you will want to, as you work through the homework, try to make note of any geometry formula that you use, because those are all fair game. Surface area of a sphere, volume of a sphere, these all show up quite often. Yeah, something using a similar triangle would be good, because those show up quite a lot. Let's do the cone. So they tell us that we've got a water tank that's in the shape of a cone. And they tell us the radius of the circle at the top of the cone here, if you like, at the base, is 2 meters. The height is 4 meters. And they say water is being pumped into the tank at 2 cubic meters per minute. And they want to know the rate at which the water level is rising at the moment when the water is 3 meters deep. So I will get the important parts of this written down. Do it together. This might be the first time we have to use similar triangles in this class, so it's another geometry thing. Water is being pumped in a conical tank at 2 cubic meters per minute. Draw the picture we want to find. How fast water is rising when it is 3 feet deep. Okay, and it was 2, 4. So copy the words down, picture. It's 2 feet. Height of the whole thing. 4 feet. And the idea is, of course, as we add water to this tank, it's going to all go to the bottom. So there's going to be a water level in here at any given moment as this is happening. In the textbook, they label this as H, but you could call it Y or Z or whatever the hell you want. And there's a lot of symmetry here, right? Like the surface of the water is also going to be like a little circle in there. I want to know how fast the water is rising. In other words, how fast H is increasing at the moment when H is equal to 3. So this gives us our want. I want to know how fast H is increasing. In other words, I want TH dt at the moment when the water is 3 feet deep. At the moment when H is equal to 3. We have a need for a variable that I haven't labeled yet. The rate of change they gave us, this 2 cubic meters per minute, what is that?
The volume.
Yeah, that's a rate of change of a volume. Now, the volume of the whole cone, the volume of the tank isn't changing, right? This tank is not shrinking or stretching, but the volume of the water in the tank is changing because I guess I should draw it. We're pouring water into this thing, right? Some guy up here is dumping in buckets, or there's a pipe pumping water in, something like that. So if I let V, I can choose or define V to be the volume of water in the tank. Then this bit of information they gave me here, the 2 cubic meters per minute, is dV dt. dV dt is 2. Oh, I do notice an issue here, 3 feet and meters. We need to make sure we're using the same units everywhere. Let me reread the problem here. Did they say, yeah, it should be 3 meters. Sorry. Meters deep. So this is a teachable moment, right? If you're given information in different units, like meters and feet, 2 different units for distance or for length, we'd have to convert everything into the same one. So if it really was 3 feet, if that's what the problem actually said, I would convert that 3 feet into meters, be a little less than 1 meter, like 0.8 meters or something. But now we've got all of the variables we need defined. We're aware of what we know in terms of derivatives of those variables, and we're aware of what we want. What I don't have is a nice geometry relationship here, something that I can differentiate through. What variables should I be trying to connect with geometry? This equation we're going to differentiate through. Don't worry about what the equation is just now, but it should involve what 2 variables? What are the two rates that we're trying to relate to each other?
V and H.
Yeah, very good. V and H. Kind of funny feature of this problem is that V didn't come with the problem, right? We had to invent it. So we want to cook up a relationship between the volume of the water in the tank and the height of the water in the tank. And the trick to doing that, to begin, let's make this over here. To get started, we need the relationship between V and H. They're both clearly changing over time. As I add water, the height's going to go up. Of course, as I add water, the volume is going up. But what is the concrete relationship between them? It's going to come from something called similar triangles. So in your trigonometry class, one of the things you guys talked about are triangles being similar or congruent. Some terminology there. If you look straight on at this cone sideways, let me draw it like that. So here's the whole tank. Since the radius of the top is 2, right? If I split this in 2, drop a line straight down there. They told me that the radius is 2, and the height is 4. Haven't quite drawn it to those proportions, but whatever. The water goes to the bottom of the tank, of course. So let me draw my water line in here. And the idea is that the height of the water in the tank is this, which is this side length. This side length, I don't know. Let me call this R, or radius, right? Or you can call it X, or you call it whatever you want. Just don't call it T. The big triangle here, what kind of colors will stand out? Already got blue. How about black? The big triangle here and the little triangle here are what are called similar triangles because they share two angles. They're both right triangles, this and this, and they both have this common intersection down here, meaning the angle down here is the same for both. And as soon as you know two angles are the same in any triangle, the triangles are automatically similar. The volume of the water in the cone, right, the volume of any cone is 1/3 times pi r squared h. So for any cone, is 1/3 times pi r squared times the height. Pi r squared is the area of the circle at the top of the cone, right? So 1/3 of that area times the height is how I remember this. Also works for pyramids. Cross-sectional area at the base times 1/3 times the height. So the blue stuff here, the water is in the shape of a cone. It's a little cone sitting inside the big conical tank. H is one of my parameters I'm interested in. V is one of my parameters I'm interested in. R, though, don't like R. I have no information about the radius. They didn't tell me what the radius is at the moment in question. They didn't give me a rate of change for the radius. So we need to get rid of R. Before taking derivatives. That's a small fib. You could actually differentiate that using the product rule, differentiate implicitly with respect to time using the product rule, but you're going to get a nastier expression. And the beauty of this is that through the geometry of the situation here, R and H are linear functions of each other. They're proportional. And that's the similar triangle argument. So the little purple triangle in here is similar to the larger black triangle here because they share two angles, or one is inscribed in the other. So draw a little partition here and say by similar triangles, the ratios of side lengths of the little triangle and the big triangle are the same. That's what it, so two triangles are similar if they share the same angles, which automatically is true if they share two, because triangles only have three angles, and have the same ratios of side lengths, meaning like the opposite over the hypotenuse for one triangle will be the same as the opposite over the hypotenuse for the other triangle. If this is 2 and this is 4, then when I divide those, I must get the same thing as when I divide little r and little h. So by similar triangles, r over h is equal to 2 over 4, right? This length over this length must be equal to this length over this length. And multiply both sides by h, you get r is equal to 1/2 times the height, h. And this is what we're going to use to get rid of the variable r in this expression. Could I get just a quick react in Zoom if you've seen similar triangles before? Thumbs up, whatever. Yeah.
We saw them a lot in trig.
Okay. Yeah, good. Yeah, we should see them in trig. I know that trig at Santa Fe is not always what it should be, so I just like to gauge it. It's not a judgment on you. It is a judgment on your trig professor. I'm just curious. Okay. So we're going to take this, use it to replace r here. That will give me just v's and h's in this expression, and then I can differentiate and do the normal thing. So therefore, v is 1/3 pi times 1/2 h squared times h. Just replacing r in that equation by 1/2 h. I'd like to clean this up before we differentiate. Let's see, that's 1/3 pi times 1/2 squared is 1/4, h squared is h squared, h squared times h is h cubed. And now we can differentiate. I've got this lump of constants out front. That's pi over 3 times 1/4 will be pi over 12. Let me just go ahead and write it. So this is pi over 12 times h cubed. So when I differentiate on both sides, I'll get dv dt on the left, pi over 12 times 3h squared times dh dt on the right. I know that dv dt is 2, and I want dh dt at the moment when h is equal to 3. So I plug in 2 for dv dt. Pi over 12 times 3 is pi over 4. H squared is going to be 3 squared times dh dt. So I'm canceling the 3 and the 12 to give me this 4. That's where this 4 is coming from, and that's where this 3 goes. The 3 squared downstairs is me, sorry, 3 squared in the bottom expression is me just plugging in 3 for h. This is true when 3, because dv dt is always 2. And now it's just a matter of solving things, right? So this is 9 pi over 4. If I start cleaning things up here, 2 times 4 is 8. And then I'm going to divide by pi, divide by 9. So that's 9 pi equals dh dt. You know, pi is in the neighborhood of 3, so this is like 8/27ths. But again, to get a meaningful taste for how fast this is increasing, might not be a bad idea to whip out your calculator. So 8 divided by 9 pi is about 0.283. Looks like 283. It's meters per second. Cool stuff, right? Okay. So that's time for today. There are so many variations on these problems, just so many different things you can do with them. The algorithm is always the same. So in the last second here, I know we're right at time. I just want to lay out the steps. So if you're working on a problem and you're stuck, you can go back, look at this list of steps and ask yourself, did I skip one of these? Did I miss something? Questions on this? Okay. So our algorithm steps. First up, read and draw a picture. Second step, define your variables. Third step, and this is one of the harder steps, is find an equation relating the variables and identify what you know and what you want in terms of time derivatives. Then you're going to differentiate. By that I mean apply d dt, both sides of your equation. And then you're going to try to solve for the desired derivative. And you may often, you will, separately solving for one of the variables left over. Like we had to solve for r in that first problem, we had to solve for y in that second problem, and then in our most recent problem, we had to use the similar triangles thing to get r in terms of h. But certainly, always first read the problem very carefully and draw a good picture. The art doesn't need to be beautiful, but the picture needs to be large enough that you can like label things and tell what's going on. You're always going to need to define some variables because it's very rare they do that for you. Finding an equation relating the variables. Sometimes here you're going to use trigonometry. Sometimes here you're going to use the Pythagorean theorem. Sometimes here you're going to use a formula you know from geometry, like for volume or surface area or something like that. Each time you use one of those, make note of it. And you know, if you're a flashcard person, make a flashcard. Just try to remember the geometry equations that you need in these problems because they're likely to show up elsewhere, i.e. on the exam. Identify what you're looking for and what you were given in terms of the derivatives of the variables that you have, and then differentiate both sides of your equation. Hopefully you'll be in a position where you can solve for the thing you want, but if you're not, go back to the original picture and imagine freezing time at the moment specified in the problem. It's very rare they'll say at time t equals 5 seconds. Usually they'll say at the time when the radius is 5, or at the time when the surface area is 10, or something like that. From that, you can solve for whatever extra bits of shit are left over in your derivative equation, and then solve for the desired derivative. Okay, that's the algorithm. And I'd be happy to work more examples with you guys if you want in office hours, or if anything you get stuck while you're working the homework, just let me know. I'm happy to work those out with you. Of course, you can talk to each other on Discord, or you can email or Canvas message me with anything you're having a hard time with. Snap me a picture of your work. It's always the best way for me to give you good feedback. And yeah, that's it from me for today, guys. Any questions before we go? Okay, this is related rates. If you want to, at the start of our next class, let me know. I can solve 1 or 2 more problems because I know after you played with them a little bit, it's often helpful to see a little more work. So just let me know at the start of class on Wednesday if there's a particular homework problem or something that's giving you a headache, or if you just want to see more examples. Otherwise, next time we're going to start talking about linear approximation, which is a very different ballgame. So work hard on these. Your homework's going to open up here in just a few seconds, and I'll see you all on Wednesday. Bye, guys.